All right, just for fun. Let's do one more where we can kind of practice this 5% rule. I know at the beginning it sounds kind of weird, but really the 5% rule is a good thing. You can use this quite a bit. You can use this, I would consider using the 5% rule, whenever I see a small k value. And by small, we mean like times 10 to the negative something power. I'd try it. They'll give us the balanced equation. Carbon dioxide is added to a closed container at a pressure of 4.6 atmospheres. Carbon monoxide is also added to the container at a pressure of 0.4 atmospheres. Calculate the partial pressure of each gas in the container once the system reaches equilibrium. Oh, I like this one. We haven't had one with gases for a while. So let's do the balanced equation. 2 carbon dioxide in equilibrium with 2 carbon monoxide and O2 oxygen gas. ICE. I love ICEs. All right, so initially, again, we said you can use pressures or concentrations. We have pressures, 4.6 atmospheres for the carbon dioxide and 0.4 for the carbon monoxide. Initially, there's no oxygen, so I'm shifting forward. Shift forward. Excellent. I know the direction of the shift. If I didn't, I would have to calculate Q. And then I would compare Q to K. And yes, you can do Q with pressures. Okay, what else do we know here? Nothing. That's fine. We know we're shifting forward. We're going to shift by the ratio in the balanced equation. So this is going to go down by 2x, up by 2x, and up by x. We're shifting forward. So at equilibrium, we have 4.6 minus 2x, 0.4 plus 2x, and x. Are you starting to kind of figure out these ICE tables where like this just becomes kind of like second nature? Like, okay, well I know I get my initial, I know the direction of the shift. I'm going to say that the shift is by x, shift at the ratio in the balanced equation. I mean, they become kind of predictable. Like you set everyone up the same way, which is why like when you get to the AP test and you're guaranteed an equilibrium problem, at least you have something to fall back on. Like if you look at it and you're like, oh brother. Well, initially, I'm going to start with an ICE table. At least if you start going with an ICE table, it gives you a little direction. Okay, so we have K. Where was it? 4.0 times 10 to the negative fifth. K is small. All right. K equals 4.0 times 10 to the negative fifth, which will be products over reactants. On the top, I'm going to have this 0.4 plus 2x. And I still need to square that because of the ratio in the balanced equation, times x to the first, all over, ooh, this is going to be fun, 4.6, minus 2x, and that's all getting squared. Woo! This is going to be a doozy, right? I mean, if I really wanted to solve this, I'm going to have like x cubed on top and x squareds on the bottom. I mean, this would really be fun. If algebra is fun for you, maybe it is. But what if we want to do this quicker? What if we have better things to do with our time than sit around and play with our calculators all day? An option. Try the 5% rule. Again, the 5% rule says that when you have a small k value, yes, we're shifting, but we're not shifting by much. K is so small that if we go products over reactants, we still have primarily reactants. So like that whole minus 2x, the amount of reactant that gets consumed, that's going to be small. So it would sure make my math easier if I just got rid of it. Yeah, we're going to consume some of the reactant, but it's going to be small. Maybe it's so small that it's kind of insignificant. Let's try the calculation without it. we can do the same thing on top. Yes, we're going to go forward and we're going to produce a little extra product. But again, it's not going forward by much. So this whole like plus 2x, let's try getting rid of it. Now you got to keep the x. I mean, the only thing that you consider canceling would be any like plus or minus x. Obviously, I have to solve for x, so I can't get rid of all of them. Boy, does this make your math a lot easier, though, right? Because now watch what happens. Actually, this is super easy. Let's give myself a little more room. I'm going to have to simplify this a bit. And one of the most common errors is that sometimes people forget that you still need to square these guys. We're just getting rid of like the minus or plus 2x. So, I mean, I'm not going to have to do the quadratic equation. I'm not going to have to FOIL any of this. But I still do need to square it. So I'm going to get something like, okay, on the top, 0.4 times 0.4, this will be like 0.16. And then on the bottom, 4.6 times 4.6, 21.16. Okay, so now let's see if we can simplify this expression. We'll cross multiply. And let's say here, I'll plug this in my calculator. I don't really care about sig figs right now, I guess. Let's go 8.464 times 10 to the negative 4th equals, and then on the top, all I really have is 0.16 times x. Wow, that's not bad at all, right? Okay, so let's divide each side by 0.16. X equals about like 0.00, I don't know, 529-ish, something like that. 0.0053. That made my math so much quicker. Rather than having to like FOIL it, and then this one I'm going to get like something cube, and it's going to be a pain in the rear, which for some of us really might be fun. And others, yeah, we got better things to do with our time. Let's see if that was a fair assumption. Okay, so we're going to plug x back in to our equilibrium set. 1, 2, 3. Gosh, that's a lot of arrows, isn't it? Okay, so at equilibrium. La la la. My carbon dioxide is 4.6 minus 2x. That x is small. I don't know. Let's just go like 4.59. I mean, man, that is small. It's almost insignificant. Carbon monoxide, 0.4 minus 2x. I mean, plus 2x, hello. How about like 0.41? And then the last one, oxygen, is x. So we could say like 0.00529. That would be atmospheres. There's not a dot back there. 0.0053 would be fine. Okay, so here would be my equilibrium conditions. Let's just quick check the 5% rule and see if this was okay. So I assumed, and then we can pick one. We can pick either one, the reactant or the product. I don't know, let's pick the reactant. So for the carbon dioxide, when I used my calculations, I just used 4.6 atmospheres. Now that I calculate the carbon monoxide, oopsie, calculated carbon dioxide, I got like 4.59. Are you pretty confident that they differ by less than 5%? I mean, if not, you can plug this in your calculator and double check. which just for kicks, let's say we do. Yeah, this is fine. They differ by like 0.22%. This was a fair assumption. So when I write my final answer, I'm just going to say 5% rule, check. Yes, I checked it. You don't always have to show work for how you checked it, but at least acknowledge the 5% rule. Just say 5% rule, check. Then that explains why when I showed my work and did my math, I did not include these two quantities. Because I knew that X was going to be really small, and I double checked, and my calculated and my assumed differ by less than 5%, way less than 5%. To be honest with you, sometimes I say that I checked the 5% rule and I really didn't. And sometimes you can just tell, oh yeah, in this case, X was super, super small. Do they differ by 5% or less? Heck yeah. I mean, I can just tell that by inspection. So sometimes I actually don't show all this work. I mean, I never really show the work. Sometimes I don't even plug it in my calculator to check. I just say that I checked the 5% rule. I thought about checking it. I thought about it in my head. Did I inspect my answer? Sure I did. I really didn't calculate the difference. But I at least did acknowledge the 5% rule. So I would always just kind of put that in your calculations, by your final answer. 5% rule, check. Then that explains why you simplified your calculations. It really is a good thing. For a while it seems kind of strange, I'd really just like to plug this in my calculator. But eventually you'll kind of see it's a super big time saver. And you do this a lot. We'll use it a ton in the next few chapters. So you'll want to make friends with the 5% rule. It's a good thing.